said, welcome to the last class of the semester, and we're going to be talking about lift and drag. So we talked about this a little bit before, but now we're going to get into the details of it. So like we said before, in external flows, we're the most interested in the net forces that are acting on a body that are imposed by the flow. And so these two forces, as maybe you have guessed, are called lift and drag. And so lift is the net force perpendicular to the flow. This is also called the cross-stream direction, which we talked about that a little bit last time. So it's, perpendicular to the flow. And it's denoted FL. So some textbooks will draw like a really fancy L, but I can't draw that, so I just do F sub L. But if you see like a curly L, it's probably lift. And so drag is the net force in the direction of flow. Otherwise known as the streamwise direction. And likewise, I'm going to denote it F sub D. And again, sometimes it's written as like a curly D instead of this. So just to kind of give you a picture of what this looks like, we talked about cars a few times last time. So if we have our nice car here and it's in an external flow, then these forces we're interested in are the drag force, which acts parallel to the flow, and the lift force. Okay, and then just to reiterate, both of these forces are exerted by the flow on the body. And these forces are due to shear stress, which is tau, and pressure, normal pressure. P. And so to start our discussion about how we're going to calculate drag and lift, I'm going to draw a nice airfoil. So I guess, I don't know if Kennesaw has like aerospace engineering, but it's kind of like very specific mechanical engineering. And you just like talk about airfoils for like an entire major. It's wild. But this is an airfoil. It's my drawing of an airfoil. And we're going to say it's in some external flow. And I'll draw a little coordinate axis here. And so looking at the shear stress and the pressure, we know, right, that shear stress acts parallel to the surface. So it's going to look something like this. So that's tau. And then our net pressure acts normal to our surface. So I'm going to draw the lines first. It's going to look something like this and acting this way. That's our pressure. So now to calculate the drag and lift on here, maybe your brain is already going that way and you're horrified, but you can integrate the pressure and shear stress variation over the area of this airfoil or whatever your object is. Let's see, let me see your question. No, there's pressure at there's a question in the chat and it says, is there pressure only at the bottom? So there is pressure also at the top. So these top lines are like this part here. So that pressure is acting still on that top part. It's just not acting from the top down, it's pushing the other way. This is like the nature of an airfoil, right? Because it's like an airplane wing and you want it to go up, you want it to have lift. So that's why they're shaped this way, so that you have this pressure that pushes it up. But good question. Does that answer it? So does that mean that there's more pressure from the bottom? Yeah, well, yeah. It means that the net pressure is pushing it up in this direction. Okay, great. Okay. Yeah, so we could integrate, which it's like not looking really great right now. You're like, this is gonna be a really difficult integration. And you'd be right. Their airfoils aren't too bad, but what if you have like a crazy shaped object? How are you gonna calculate, how are you gonna integrate over the area? It's gonna be really hard. It's gonna take a lot of time. And not to mention, it could be really difficult to measure the shear stress on a surface. Pressure is kind of difficult to measure, but not like terrible. But shear stress is really, really difficult to measure. So getting all of this information in order to integrate could be really difficult. And as engineers, we don't have time for that. So instead, we have another method, and that is using lift and drag coefficients. And these, you may have gotten them when you did, I don't know if y'all did dimensional analysis, but these come up with dimensional analysis. So your lift coefficient is denoted C sub L, and it is the lift divided by 1/2 rho u squared times area, where this u is your upstream velocity, density is the density of the fluid, FL is your lift, of course, and A, which area that is, we're going to talk about in a minute, but it is an area. So, and this should just be singular. So likewise, we also have a drag coefficient. And so that is C sub D, and it's pretty much the same thing, except it's drag force divided by 1/2 rho u squared A. So generally, this is what we use unless, we somehow know the pressure and shear stress distribution and know the area of our object. We'll use these instead. And so CD and CL are usually obtained from boundary layer analysis and experiments. So as you'll see throughout this lecture, there's this kind of stuff. You end up going and looking in tables and finding these coefficients depending on whatever kind of body you have, what the situation of your flow is, and then using that to calculate the drag force or the lift force, or maybe the velocity or whatever it is you're looking for. And so these two coefficients are a function of Reynolds number, the shape, so geometry of your body, Mach number, which is a measure of the compressibility, the relative roughness, which you probably, or that's the surface roughness, which you probably did when you did internal flows, and then also Fruit number, which is relating the speed to gravitational effects. And so we could get into all of these, but for time's sake, we're actually just going to concentrate on Reynolds number and shape. Okay, any questions so far? Okay. Again, definitely jump in anytime with a question. Oh, right. I told you we were going to talk about areas. Now is when we're going to talk about the area. So this area in these equations at the bottom, there's two areas that we could take. You either take the frontal area, which is a projected area as seen from looking in a direction parallel to the flow. So when I think of this, I always imagine myself like standing on the flow, like on a little fluid particle and looking in the direction I'm going. So if you come back up here to our little car, right, it'd be like you were standing right here and looking this direction. And then, so the projected area is if you held a flashlight standing here, you've held a flashlight directly looking at this car and it produced some shadow. That shadow would be a rectangle, not including the wheels. It would be a rectangle. And so this is your frontal area of this car here. Okay, and we're going to do an example. If you're confused, we're going to do an example. So hopefully that will clear it up for you. Okay. And then the other type of area that we can have is called the planform area. And so this is again projected area. As seen from looking in a perpendicular direction to the flow and from above. So again, if we go back to our car really quick. So the planform area would be the projected area if you were standing up here and looking in the perpendicular direction. And so again, if we cast a shadow, again, we'd have this rectangle, and that would be our area that we're interested in. Okay, so now I'm going to do, does anybody have questions on that, or do you want me to do the example and then maybe you can ask questions? If anybody has a question, just pop in. I am actually like the worst at geometry. It is my least favorite part of math and engineering in general. So all of this it takes me a minute to like wrap my brain around it. So in the interest of that, let's do an example. So we're going to look at an ellipsoid. So we have a flow, U, and then we're going to have this nice ellipse. It's going to have a length L. This height dimension is D. And then B is the length into the page. Okay. So the frontal area, again, we're going to be standing right here and looking this way for the frontal area. And so I'm interested in this part, this front part area and what that's going to look like. And so that's going to be the dimension into the page and then the height. So this is BD. All right, and then, sorry, go ahead.
Hello?
Yep.
So am I standing like behind the ellipsoid and looking at from behind?
Yes, so you're standing where the flow is coming from and looking directly at the ellipsoid.
Okay.
And so for this one, it wouldn't matter if you were standing like over here and looking this way, but sometimes like if you have an oddly shaped object, then it might make a difference.
Is it like sort of looking at a cross-sectional area or just like the surface?
It's the projected area. So again, it's like if you're standing here at this spot and you shone a flashlight on directly in this direction, parallel to the flow on this ellipsoid, and you looked at the shadow that caused, it would be this rectangle. Let me draw it. Get rid of this. The shadow that it would cast would look like this, where this would be D and this would be B.
Oh, okay. Yeah, that makes more sense.
Okay. Good. Okay. And the planform area here, and again, so now for planform area, we're going to stand up here and we're going to look down and turn our flashlight on and see what shadow it casts. So we're looking at this part, and it's going to cast a shadow, again, B, and this time L. So planform area is BL. Okay, I know this is confusing if you're like me and you hate geometry, or maybe even if you don't. So I have one more example for you, and that's a circular cylinder. So now we have you, and this cylinder is going to be oriented a little differently than what we're used to. It's going to be the long way is along the direction of the flow, and it's got a diameter D. Okay, so now I'm going to let y'all think about this, and I have a Slido. I have another poll for you. If David, would you mind putting that in the chat for me? Perfect, thank you. So my question is, what is the planform area of this cylinder? And so I'll go back to this picture. So y'all can think, well, let's put them both on one page. How about that? All right, so most of y'all who have answered so far have gotten it right. It is BD, so planform area is BD. And again, planform, we're standing here, we're looking down, and that shadow it's cast is going to be a rectangle, that's BD. Some people put BL, but I assume by L you mean D, so I'll take that one. Someone said pi over 4b squared, and I'm guessing the curve part is confusing you a little bit, but again, it's a projected area. So if you shone your flashlight on here and looked at the shadow, it would just look like a rectangle. So good job, guys. And so next question. So I don't have a Slido poll for this because I only get 3 for free. But does anybody want to chime in and say what the frontal area is?
Would it be like a circle? Or
Yes.
maybe okay.
Yeah, you're exactly right. It would be pi over 4d squared. So again, frontal area is standing here and looking this way, and then we just have a circle. Good job. All right. And so lucky for y'all, usually this is pretty standardized. So if you go look up on a table, they'll tell you like this is the area of interest. But every now and then, especially if you're designing your own system, you might need to make this decision. So it's really kind of like you have to pick whichever area is most relevant. And that can depend on a lot of things like the aspect ratio. And yeah, so that's just a little bit of intro into the areas. But usually it's like pretty straightforward of which one you should use or standardize. Okay, so now we're going to start talking about drag. All right. So if we go back up here, way back up here, right? I said that these two coefficients are due to a bunch of different, or they depend on a bunch of different aspects, and we're going to concentrate on Reynolds number and shape. So I'm going to start talking about drag in the terms of shape dependence. And so when we talk about shapes, a lot of the time we talk about aspect ratio. And so usually that means, so it's L over D. So it's the ratio of the length of the object to the depth or the height of it. And if you remember from Monday, I forgot what day it was for a second. We talked about both blunt and streamlined bodies. And turns out that they will have really different behaviors with drag depending on if the body's blunt, if it's streamlined, or if it's somewhere in the middle. So if you remember, for our blunt body, we talked about a circular cylinder. We're going to draw that. And so this circular cylinder has a small aspect ratio. And so blunt bodies usually have small aspect ratios. And for our streamlined body, we talked about a flat plate. And so this, as you can see, will have a large aspect ratio. And so again, these, you can look these up in tables. So in the textbook I'm using, there's like a ton of tables for different shapes, and it literally just tells you what the coefficient is for either of them. So I'm not going to rewrite the table for you, but I do want to give you an example of how important the shape can be on the amount of drag. So if we have a sphere that has a diameter d that's in an external flow, and so in speed, a velocity, fluid velocity of u, and a density of rho. So this is our circular cylinder. For this circumstance, the coefficient for this, or sorry, I think I said sphere, but I meant circular cylinder. So for this circular cylinder is 1.2. And if we have an airfoil that has this dimension of 10d, so it's 10 times bigger than this circular cylinder, and it's in the same flow, so same velocity, same density, this has a drag coefficient of 0.12. And both of these end up having the same amount of drag. So you can have something that's 10 times bigger, but it's shaped more streamlined, and it could have the same drag as something way, way smaller. So this is just really to, describe how much the shape of the body matters for drag. Okay. So I'm going to come back to this actually, but for now, let's move on to Reynolds number dependence. And just to remind you, Reynolds number is density, velocity, some length, which is either d or L, over viscosity. So for Reynolds numbers, less than 1, so for really low Reynolds number flows, there is a balance between viscous and pressure forces. So what that means is, because a lot of times, we'll like, oh, this viscous force is really, really small compared to our pressure force, so we'll just ignore it, or vice versa. But in this case, for low Reynolds number flows, you cannot ignore either of them. They're very similar in magnitude, so they're important to the flow. And in these cases, our drag force depends on velocity, the length scale that you're working with, and the viscosity. And if you do some dimensional analysis on this, you end up getting that FD equals C times mu viscosity times length times velocity. And I just want to point out this C is not the drag coefficient. It's different. The textbook I was using C, and I was like, why C? Can't we go do something else? But I didn't want to change it. So yeah, so it's different than the drag coefficient. And this is actually, it accounts for the shape of the body. So it'll be different again for different shapes of bodies. And so if we do a little bit of analysis on this, we can see that the drag coefficient, right, from our definition earlier, this is the drag force divided by 1/2 rho u squared A. And if we plug in what we got from dimensional analysis, we get that this equals C mu L u over 1/2 rho u squared. And we're going to take our area to be L squared. And we can simplify that to 2C over Reynolds number. So someone in the chat asked, will that value be usually given? Which value, the one of C? Yes, okay, yeah. So that one is something that you could look up again. So they have it's pretty standard for a bunch of different standard shapes. So if you have a really weirdly shaped body, you might be a little out of luck. But if you have like a sphere or a cylinder or something you can approximate as that, it'll be something you can look up in a table, which would be provided for you. Which actually, fun fact about weirdly shaped objects, I, as you know, am very interested in pollen. And pollen can be crazy different shapes and sizes, and it makes it really, really difficult to measure the density of it. And so back in like the early 2000s, there's some really clever people who devised a way to use this to do an experiment where you drop a pollen in 2 different viscosity fluids, and then you do some magic, not really magic, but you do magic with the equations, and then you actually end up factoring that C out, because I don't know what C is for pollen. So you end up factoring that out, and then you can figure out what the density of your pollen is without having to rely on a really inaccurate shape factor, which is exciting for me. Hopefully it's also exciting for you. Do you have a question?
Yeah. So the top part where FD is?
Yes.
Is that mu times L times U, or is that 2 U's?
It's mu as in viscosity.
Okay. So how did the U squared on the bottom get canceled out? Oh, it's not IE. Oh.
Yeah. And so I plugged in Reynolds number, which is rho u L over mu.
Okay.
Good question. Okay. All right. So that is low Reynolds number. And so that one is pretty standard. Look at the shape factor or come up with a clever way to get around the shape factor. But then as you start to increase Reynolds number, things start to change a little bit. And so as Reynolds number is increased, so this is when boundary layers start getting really important. So boundary layers have a really big impact on drag. So I'm going to bring back our good old friend, circular cylinder. And again, I'm going to draw what this looks like in, so this is going to be a high Reynolds number flow. And so we know from this, from what we talked about on Monday, that we're going to have a boundary layer in this, the very thin boundary layer. It's going to look like this. This is our boundary layer, which, oh, I think I forgot to say that I often write BL for boundary layer just to save some time, save my hand a little bit. And then if you remember, we also have, when the Reynolds number is high, we get a separation point in our boundary layer. And here our flow separates. So between the dotted line and the blue line is our boundary layer, and then below it is, we have some backflow. And it's in our wake. So the boundary layer starts becoming really important for drag because of this separation. So at the separation location, the shear stress at the wall is 0. Because your flow is like totally departing. So there's nothing to cause a shear stress there. And what happens at that separation location is that the pressure on the rear half, so, right, if we drew a dotted line, rear half is this half back here. So the pressure on the rear half is significantly less than the front half. So if you remember also back to Monday, we talked about D'Alembert's paradox, where we said, well, this pressure distribution must be the same everywhere because it's in the same flow, so we should be good and there shouldn't be drag. But then people measured it and there was drag. So this is the reason why. It's because the flow separates because of the high Reynolds number and because of that viscosity in the boundary layer. You end up having an unequal pressure distribution, which causes a net force, which causes your drag. And so that is what took them 200 years to figure out. And so again, this leads to a high drag due to pressure. And then again, just to note, because this flow is inviscid outside of the boundary layer, the shear stress doesn't contribute much to drag. So it's mainly just a pressure drag. It's just really small compared to the pressure. Okay. So what we've talked about so far is how we're still in drag, is how the shape of our body and also the Reynolds number of our flow will affect the drag. And what's important to note here is that we can't separate them necessarily. Like we can't say, oh, well, this is a circle or this is a cylinder, so I'm going to look it up on this table and it's always 1.5. That's always the coefficient. You also have to account for the Reynolds number. So they can't be taken as individuals. It's kind of like a composite thing. And so I'm going to go actually to here. Where is it? There it is. Okay. So this is an example of the kind of tables that you can use to determine your coefficient. And this is the drag coefficient for differently shaped two-dimensional objects and compared at different Reynolds numbers. And so I'm going to talk you through some of these. So at the top here, we have very blunt bodies. This is a flat plate, but as you can see, it's oriented differently than what we're used to. And then as you go down, they become, a little bit more streamlined with the circle until you get all the way down to this flat plate that's parallel to the flow, and then this is very streamlined. And so as you can see, the very blunt bodies, like this flat plate perpendicular to the flow, their coefficient of drag doesn't change at all with the Reynolds number. It's just a flat line. And the reason for this is because when you're that blunt, the flow will always separate, no matter how fast you're going or how big your plate is. It's always going to separate. So you're always going to have that crazy pressure differential, and then the shear stress is just negligible. So it's always going to be the same. It might change like very, very small amount, but nothing substantial. So this happens because it always separates. And then as you move down and you get more streamlined, you might notice, it happens pretty drastically that you're at first you still have a constant drag coefficient with the circle, and then it drops. And the same with the ellipse, it's a little more wavy, but then it drops. And then the airfoil and the flat plate, we're changing the whole way. And then these actually kind of start to increase. The coefficient starts to increase as you're increasing with the Reynolds number, which is interesting, right? You might be asking yourself, why the heck is that happening? So just going to write that down, what I just said. As the shape gets more streamlined, we see a sudden change in the coefficient of drag at certain Reynolds number. And this happens because at the higher Reynolds number, the boundary layer becomes turbulent, and this significantly changes things for us. So I'll go back up here, and I just want to note that this drop happens at different places for different shapes. So whatever that critical Reynolds number is for this change, it will depend on your shape. Okay, so for blunt bodies, we see a decrease in the coefficient of drag because the turbulent boundary layer separates later. So I'm going to draw again one more time. I think it's the last time for today. Nope, I have more circular cylinders coming, but I'm going to draw the circular cylinder. We know it looks like this, and we have the boundary layer. Ooh. Like that. And then we have, so for lower Reynolds numbers, right, before we get turbulent, we'll have the separation point here. So this is lower Reynolds number. But as you increase the Reynolds number, and say your velocity is increasing, then this separation point starts to move. Let me draw. And so now, if you remember, right, we talked about that pressure distribution and how because it separates, it causes a huge differential between the front and the back of how much pressure is being applied. But now at the higher Reynolds number, that pressure difference becomes smaller because this area becomes smaller, like the separation region becomes smaller. And then that will give you a lower drag coefficient. And so I'm going to write that down again. So later separation leads to a smaller pressure difference, which leads us to a smaller drag coefficient. So you can see why going faster is sometimes better because you have less drag. All right, now for streamlined bodies.
Hello?
You have a question? Yeah, go ahead.
So I'm looking at the shape. So is that like the airflow right there on the left one?
Sorry, say it again.
Can we look at like an airflow, one of your images from earlier?
Yeah,
that one.
Oh, the air. Oh, yeah. Okay, yeah. The airfoil.
So like below it, would that be like laminar flow, and on top would be like turbulent? How does this work?
So for an airfoil, it doesn't separate as easily. I'm trying to think if it would be laminar or turbulent. So yeah, so for actually, you're leading me right into my next point, but I can, yeah, this good question. Good transition question. So for an airfoil, right, for our blunt bodies, we saw a separation. For our streamlined bodies, we don't really see a separation. And so that whole pressure differential thing doesn't really apply, at least not because of separation. Like there's still a pressure differential, but it's not like as significant because we're not separating on the flow. But instead, so you see this increase when you're streamlined, at this certain point, like you really see that increase with the flat plate. And that happens because turbulent flows have higher shear stress. And so that's what's causing, it's like such a big increase in your shear stress that it's causing a higher drag coefficient.
Oh, okay, so it's the shear stress.
Yes, yeah. So blunt bodies, it's the pressure, and then streamlined bodies, it's the shear stress because it doesn't separate.
Okay, that makes sense.
Okay, awesome. Good question. And I'm just going to write down everything I just said so y'all can have it in your notes. So for streamlined bodies, CD increases because the drag is due to shear stress, and turbulent flows have greater shear stress. Okay, so I'm going to do an example next, but does anyone have questions before I do that? Okay, so I'm going to go ahead and do an example. Oh yeah, I have that in here. There we go. Okay, and again, so I'm using a different textbook than y'all, so this has a problem number on it, but it will not be the same. Yeah, I don't even know if you have it in your textbook, but it won't be the same chapter number or anything. Okay, so in this problem, we have fluid that flows past a flat plate with a drag force FD1. So I'm going to draw that really quickly. And so if the free stream velocity is doubled, will the new drag force FD2 be larger or smaller than FD1, and by what amount? So if we write this out, so we know that the drag force equals 1/2 CD rho U squared A. And again, so I'm just taking this from our definition for the coefficient for drag. And so we know FD1 equals 1/2 CD1 rho U1 squared A. And FD2 equals 1/2 CD2 rho U2 squared A. So the problem told us that U2 equals 2 U1, so we can plug that one in. We're going to assume it's the same fluid, so our density will stay the same. It's the same plate, so our area is going to stay the same. So the only thing we need to find out here is CD2. So, David, could you post the link to the poll again? Actually, I think I have it. There we go. Okay. So I just put the link for the poll again. And my question for you, using this figure that we just went over, how do you approximate CD if the velocity is doubled? And I have that poll open for y'all. And again, just remember we're working with a flat plate parallel to the flow. All right, in the interest of time, I'm going to go ahead and share all the correct answer. So it actually is that CD doesn't change very significantly. And it's a little bit confusing, but it's because if we look at this, right, Reynolds number is UD over, that's kinematic viscosity, nu. And so if it changes, if our velocity doubles, then basically Reynolds number 2 is twice our Reynolds number before. So, and we don't know what that is, but let's say, for instance, it's 10 to the 4th is our original. 1 times 10 to the 4th is our original. If we double that, then it's 2 times 10 to the 4th, which is like right here on this x-axis. And so it's a little bit of a change, but it goes, you can see the scale is 0.01 to 0.1. It's really not very significant. So the answer is actually that it doesn't significantly change. Any questions about that before I go back to the, y'all can still see my screen, right?
Yeah, we can see it.
Okay, good. I always get scared when it says working offline. Any questions about that? Okay. Go back here. So now we know that CD1 equals CD2. So now we can just plug that in and solve. So if we divide these two equations by each other, FD2 over FD1, we end up getting 1/2 CD rho U2 squared A over 1/2 CD rho U1 squared A. And that, everything cancels out until you have U2 squared over U1 squared. And of course, we know that U2 is 2E1. So you get this to be equal to 4. So if you double the speed of your flow, you increase the drag by 4 times. So it's not necessarily a one-to-one comparison for a flat plate. Again, Reynolds number and the body geometry have to be taken together. We can't isolate them and separate them in order to consider drag. Okay. I have another example for you. Is there a question?
Yeah, real quick. Do you mind scrolling back up to the problem statement? I think I just wrote it down wrong.
Yeah, sure.
Oh, I see. Okay, D2, D1. Got it. Thank you.
No problem. And I have another example problem, and evidently I forgot to put the screenshot in here, so I'm sorry about that. But for time anyway, I'm going to move on to lift, and then if we have time at the end, I will pull that example back up. I'll figure it out, and then we can do it. So, okay, I'm going to go back to my main thing now and go to, okay, so now we're going to talk about lift. All right, so for lift, the symmetry of our body is incredibly important. So I think this is the last time I'm going to draw a circular cylinder. There it is. So again, we're going to have a circular cylinder, and we know we have a drag force here because we just talked about that in extreme detail. So what about the lift? And so this will be acting in the y direction, as we know. And so I just told you symmetry is important. So again, one more time to the pole. I want to know, do you think the lift force on this symmetrical body will be, will there be a lift force on this symmetrical body? So I'm going to go ahead and share all the answer. So the correct answer is actually no. There will be no lift on the symmetrical body. And that's because, lift acts in the vertical direction. And because it's symmetrical, there are going to be equal. So if we draw the streamlines here, we're going to draw our boundary layer. We're going to draw our streamlines. Right? This is what it looks like. So from front to back, which will affect our drag, we have asymmetry. And so we have that pressure gradient, which is going to cause our drag. But if you look at the top and the bottom, it's exactly the same. It's symmetrical. There's going to be no difference in pressure, no difference in shear. And then they all cancel out, and then your lift is 0. So symmetrical bodies will not fly. The catch is here, like if you have a symmetrical airfoil, if your velocity is coming in at an angle instead of straight on, then you will have lift. So no matter what the shape of your body is, if you angle it so that it is symmetrical, you won't have lift. Okay. So with drag, we talked about both shape and Reynolds number. But as it turns out, Reynolds number doesn't actually affect lift quite as much. So the most important factor is shape. And again, so I'm going to write down the coefficient for lift just to remind you. So it's the same as drag, but with lift instead of drag. And then, so most devices designed to produce lift such as airfoils, which we've talked about a few times now, or the spoilers on a car. These operate in high Reynolds number regimes. And in these regimes, our lift is mostly due to pressure. And just to look at this, I'm going to draw another airfoil for you. Since, you know, if you end up working with lift, there's a good chance it's either going to be with like putting something in the air or with cars. So if we have an airfoil that looks like this, the common length used is C, so it's like the front to back, and this is called the chord length. And we talked about areas a lot at the beginning. So for these airfoils, they're usually thin. So the custom is to use the planform area. Which is, so B is the width into the page for this. And so your planform area is going to be BC. Okay, and then also as a general rule, CL, the lift coefficient, increases, and the drag coefficient decreases as the aspect ratio, which again, to remind you, is the length over the depth, increases. And so for this reason, long wings are better. So a long wing will have a really high aspect ratio. So that means that you're going to have high lift, which is good if you're on a plane, you'd like it to get off the ground, and it's going to have low drag, which is going to make it fuel efficient. Okay, so I have an example problem for you next, which I did actually take a screenshot of, so we're good there. But does anybody have questions before I do that?
When you say long wings, you mean like coming out of the paper?
Yeah, so if you picture yourself like sitting on an airplane on on the seat by the wing and looking out, it's really long in that perpendicular direction from the plane, and that's the direction where you want it to be long.
So what would happen if we make it long in the other direction, like from left to right?
So if you did it that way, so if you'd basically have a smaller aspect ratio, so then you'd have less lift and more drag. So it might be harder to get off the ground.
Okay, but it's kind of dumb idea, but so from like, I guess when I used to make paper airplanes, how come when I have like those longer wings from front to back, how come they fly a lot easier?
Oh, I see what you're saying. So I'm not a paper airplane connoisseur. I will admit that It might be because like having drag sometimes gives you a little bit more control, and paper airplanes are very, very light, especially compared to big metal airplanes. So I have a feeling that probably has more to do with how light they are. So it's like, it's a little bit like you have a little bit more wiggle room. I mean, again, I haven't made many paper airplanes in my life, but I feel like it'd be a little harder to make it like the long parts poke outwards in a paper airplane.
Oh, okay.
So maybe it's just construction limitations. But again, I haven't made very many paper airplanes in my life.
All right.
But it's a good question. It's interesting. Okay. Any more questions? Someone asked, so it acts more like a parachute. Could you give me a little more detail about what are you referring to? The paper airplane? The paper airplane. Yeah. So if you have, parachutes have lots of drag, right? Because you want them to stop. That's the whole point of a parachute. So, if you increase your drag, I guess you could say you're acting. Oh, I see what you're saying, because paper airplanes have to land essentially. And so the drag is giving you a little bit more control over where you're going. Maybe that could be it. That's interesting. I don't really know the answer, but I think that you're on the right track there. Good questions. Paper airplanes are fun. All right, so I'm going to go ahead and do the example. Okay, so for this, I'm going to zoom in a little bit, I think, or maybe I'll just make this bigger. There we go. So the problem is in 1977, the Gossamer Condor, which is shown in the picture, won the Kremer Prize for being the first human-powered aircraft to complete a prescribed figure-8 course around 2 points. And they give you some data, including the flight speed, the wing size, the weight of the airplane, the drag coefficient, and importantly, the powertrain efficiency. So that's whoever's up there pedaling, how much energy he puts in. Only 80% of it gets to actually move the airplane and overcome that drag. And so it wants you to find the lift coefficient and the power required by the pilot. So I'm going to start this problem by writing down the knowns. So they give us the flight speed. We can calculate the area from what they've given us. And we're going to assume that the density of our fluid is just air. So we're going to use 2.38 times 10 to the negative 3 slugs per foot cubed. Hopefully you all have worked with slugs before. It's like my least favorite unit, but it's fine, English units. And then we're also going to assume steady flight conditions. So basically nothing's accelerating, or your air isn't accelerating at least. Okay. And then part A, it wants us to find the lift coefficient, which we know is the lift force divided by 1/2 rho u squared A. And so if I look at this, I know that the only thing I don't know here is the lift. And so to find lift, anybody have any ideas on how we could find the lift based on what we've been given? I don't have a poll for this. You can just put it in the chat or shout it out. Ah, David is a paper airplane connoisseur, so there you go. Anybody have an idea for how to find lift? So the question in the chat is, are we using the formulas from before? So I think this is the only formula from before, unless there's a different one you're thinking of. For FL. Let me see. I still think I don't know which ones you're talking about. Me? Okay, I'm gonna go back here. So we're looking for the lift force, right? So we've got our airplane, and we know lift acts in the vertical direction. And the only other force we're going to have, because it's steady, right? There's nothing pushing, no other like airflow is pushing down from the top besides our steady flow. The only thing we have to worry about is weight. And so, again, we're assuming we're not climbing altitude. So that was kind of an assumption you would have to make. So then you could say that the force is balanced and FL equals W, which is given in the problem as 210 pounds. Does that make sense to everyone? Anybody have a question? Okay. So now we know FL, so we can easily solve for the lift coefficient. And I'm just going to move that 2 up here. So we have 2 times 210 pounds divided by 2.38 times 10 to the negative third slugs per foot cubed times 15 feet per second squared times 96 feet times 7.5 feet. Does anybody want to calculate that for me? Oh, and I'm going to do, I don't know about y'all, but I always have to work out my units. So I'm just going to do that. So I know I have, especially when there's slugs. So let's see. This is going to cancel. And that's it for now. So we have pound second squared over slug foot. And then we can convert 1 slug to 1 pound second squared per foot. And then everything cancels how we want it to. Yep. And now we're dimensionless. Happy. Okay. Has anybody, in the time it took me to cancel all my units, has anybody calculated this? $16.3. Anybody else get? Okay, somebody else got 1.09, 16.3. Anybody else? All right, so the answer is actually 1.09. So maybe check your, I think of how, did you square the 15? Maybe that's where it came wrong. Aha, there you go. All right, the sneaky square. First time I did this, I actually also forgot to square the velocity, so you're not alone. All right, so for part B, it wants us, let's go back up to the question. It wants us to find the power required by the pilot. Okay, so here power is force times velocity, but they give us some more information in here about the efficiency. And so the efficiency is going to play a part here. And so does anybody know how to apply efficiency to this equation I have written down? Like, where would I put it in this equation? Yeah, so it's it is the efficiency of how much work you put in to the actual power that you get out. Coefficient of P, yeah. So I think you're all saying the same thing in different ways. So you would say eta p equals F times U. All right, and then this F this time is going to be our drag force. So it tells us the power to overcome drag. So that's how we know we're going to use drag force. And this ends up being 1/2 CD rho U cubed A. And so this is why you're like, oh, that's why they gave me the drag coefficient to begin with. So we don't have a lot of time, but if you plug in numbers, I'll just do it really quick. Okay, 0.046 times 2.38 times 10 to the negative third slugs per foot cubed times 15 feet per second cubed times 96 feet times 7.5 feet divided by 2 times 0.8. That's our efficiency. Okay. And then units again. So we're going to have, see, this foot cubed and that cancels. So then you have, we're going to transfer 1 slug to 1 pound F second squared per foot. And then we want our final answer to be in horsepowers. So we do horsepower divided by 550 foot-pound per second. And I'm going to cancel all these things and make sure I did it right while y'all calculate this. Feet, huh? Yeah, we're good. Okay, did anybody get the answer? Oh, I'm over by a minute, so I'll just give it to you. Sorry, everyone, of 0.302 horsepower. Oh, you're off by a factor. Okay, so sorry for going a minute over. Thank you again for having me as your teacher. I really enjoyed it. I hope you learned a lot. And
thank you.
You're welcome.
Yeah, thank you so much.
Thank you.
Thanks.
Have a good luck on your finals.